Hello friends, in this video, we are going to talk about an unusual function known as the Dirac Delta Function. This was invented by the famous British physicist Paul Dirac in 1927 as he was developing his own formalism of quantum mechanics. It has the remarkable property of being able to pick out the value of an arbitrary function at a particular point. We can understand why this works by looking at the discrete analog of this integral. An integral is actually like a sum, and the delta symbol is the discrete version of Dirac's function. This symbol is just the Kronecker's delta, which is defined like so. It has the value of 1 at the chosen point when I equals j, and 0 everywhere else. As a result, it is not surprising at all that this is able to pick out the function f at the point xj. Xi's are a set of regularly spaced positions along the x-axis. These points form a one-dimensional lattice. We first assume that the lattice spacing delta x is finite. Each point on the lattice is then notated by such a right-pointing bracket. These are actually column vectors representing discrete positions along the x-axis. For the position xi, only the corresponding entry in the column is non-zero. Dirac calls such a vector a ket. An arbitrary vector, which may not represent a specific location, is represented by a column with complex entries. These entries are indexed by the discrete positions. By these definitions, any column can therefore be written as a linear combination of the position kets xi's. Thus, the entire set of xi's covering all the discrete positions forms a vector basis. As we know, any linear combinations of vectors gives just another vector. Therefore, this column is also a ket. What do these vectors actually represent? Let me first tell you what they are not. They are very different from the familiar position vectors in 3 spatial dimensions. In fact, psi represents the state of a particle along just the x-axis, so there's just one spatial dimension. But it does have an infinite number of components associated with every discrete positions along the x-axis between minus and plus infinity, while the position vector only has 3. These infinite number of components live in some kind of abstract space and not in a real 3D space. These components are actually probability amplitudes, because their absolute square are the probabilities of finding the particle at the associated positions, xi's. All these are part of the formalism of quantum mechanics, and all states of quantum systems can be described by columns like this. In this video, this is as far as we go with our discussion of quantum mechanics. See the link in the pinned comment below for my video series on quantum mechanics for a more complete introduction. For now, you can simply think of these kets as just notations for columns of complex numbers. To every column, we can define a row. This is represented by a left-pointing bracket known as a bra. For a general column, we get its row by taking a transpose followed by a complex conjugation of its entries. This is known as a Hermitian conjugation. Suppose we have a cat and a bra, representing two discrete positions. We can see that the dot product of these two is just the Kronecker's delta. This is known as a bracket. This defines the inner product between two vectors. This equation is known as the orthonormality condition. The ket xi is the state of a particle located at the position xi, so we call it the position state. We want to describe all the possible positions on the x-axis with these states. That is, we require that this vector basis forms a continuum, and we do this by taking the continuum limit. We make the points so dense and the spacings between them so small that they cover the entire line continuously. The discrete set of states that goes with each point also forms a continuum. As a result, the lattice points cover the entire x-axis, and we replace the discrete position label by the continuous position variable x, and the corresponding position state by ket x. Ket x is a continuum state that represents the particle being in a definite position x on the x-axis. But how do we relate the discrete states to the continuous ones? This is actually quite simple. Recall the discrete analog to the equation which defines the Dirac Delta Function. If we can find some kind of continuum limit which brings us from the discrete expression to the continuous one, then we are done. The definition of an integral from calculus provides a clue. We can introduce a continuum limit here. This allows us to form a Riemann integral. The function f evaluated at xi can be mapped onto fx, and fxj onto fx prime. This then allows the limit function to be identified with the Dirac Delta Function. This is a useful definition of the delta function, and will allow us to derive all its properties. We can now see what this function really means. Going back to the question of mapping the discrete states onto the continuum. Recall that the discrete states satisfy this orthonormality condition. We can map this directly. Then we can use this to define the continuous position states. Let's use the definition of the green box. The blue box can be turned into the red box if we divide by delta x. This allows us to define the continuum states in terms of the discrete. So we can see the delta function as the definition of the orthonormality of continuous position states. This is actually the reason why Dirac invented them. This procedure, where we take a continuum limit to get continuous objects from their discrete versions, works for any continuous variable, not just position. Let's look at an arbitrary state on the x-axis. We can take the following continuum limit. Applying the blue box to the red box. We can write psi I over the square root of delta x as psi x. This is known as a wave function. In the green box, we have the continuous representation of a state on the x-axis. The absolute square of the wave function, psi x, can be interpreted as the probability distribution over position x. This is clear from its definition in the yellow box. Let's look at some properties of the delta function. Just from its definition, we have the function is only non-zero at a single point, x prime. As the continuum limit is taken, its value goes to infinity at x equals x prime. This is how the Dirac Delta Function is defined in many physics textbooks. The delta function is also symmetric in its argument. This follows directly from its definition. It inherits this property from its discrete parent, the Kronecker's delta, which is symmetric in its indices. Let's look at an useful application of the delta function. Suppose we are integrating over an arbitrary function gx, but we only want to include points that satisfy the constraint in the white box. This can be done just by inserting the following delta function under the integral. It is easy to see why this works because the delta function is only non-zero when its argument is 0. So only points that satisfy the constraint fx equals 0 will contribute. Can we understand this in terms of a discrete function, in the same way we did for the definition of the delta function? A direct application of this definition would treat f as a variable. The Kronecker's delta is only non-zero when f is equal to 0. Let's identify the delta function in the yellow box with the blue box. This can be achieved by the following mapping. X is identified with the discrete position xi. F is just the value of f at xi. And for the Kronecker's delta, the integration measure delta f is given by Let's do the substitutions in the green box. We take the absolute value of delta f since this is an integration measure and must be positive. Thus we have derived delta fx as the limit of its discrete counterpart. Let's hide this limit just to simplify our notations. Now we look at our integral again. Writing this as a sum, we have this delta symbol will pick out all the points satisfying the constraint in the sum. And the sum is now just over the roots of f. For these terms, the delta symbol is equal to 1. we get the derivative df dx evaluated at the roots xr, denoting this as f prime. This equation allows us to evaluate any integral which involves the composition of an arbitrary function f with the delta function, often to impose constraints like the one in the yellow box. We can use this equation to find an explicit expression for delta of fx by using the basic property of the delta function in the green box, applying the green box to the yellow box, and bringing out the integral. Since gx is an arbitrary function, this immediately implies that the two functions in the red boxes are equal. Thus, we have an expression for delta fx in terms of delta x. This often comes up in physics, especially in quantum mechanics. This is the key result of this video.